start a little bit about the Bayesian inference. Let's see if we can cover this today. And then the last topic will be like different ways to give priors. Okay, so the one that we're doing right now is using the weakly informative prior that we're giving independent priors for each of the parameter, and then they're all weakly informative. So to make a Bayesian inference, like say in the past, we talked about hypothesis testing, credible interval, and then making prediction, right? So in simple linear regression or regression in general, you can also do similar things along the lines. So one thing we like to do for a regression model is to simulate like the model fits from the regression model that you estimated. So what we mean by that is, well, equation 16 generically gives you the relationship between the expected value, right, and the predictor. That's what we have seen so far. So if you look at equation 16, you can actually think about each pair of the beta 0 and beta 1 is going to correspond to a line in the space of x and y, right? So this is the relationship between x and y. And we know that when we say each pair of this value, so remember the fits that we had before is what, 5,000 draws for each of the parameters, right? So that means you have 5,000, actually not just pairs, the triplet, because you have beta 0, beta 1, and sigma, okay? But if you only focus on the mean, then it's only about beta 0 and beta 1. So you have, like, say, 5 pairs of 5,000 pairs of beta 0 and beta 1. So in fact, you are fitting the line 5,000 times. That's what it means, because you have that many draws, okay? So that gives us the power. So remember, in Bayesian inference, in general, and the approaches, you always do things based on simulation, and then you have draws about the parameters. Then that actually generally empowers you, I think, to do any kind of further simulation, either through prediction or anything else that you can think of. So this is, well, we have 5,000 draws of the posterior distribution of the different parameters, so you can actually simulate fits based on those draws. So one thing you can do is, well, if I just take the posterior mean and the mean of beta 0 and beta 1, and then, well, if we plot that line, that can maybe give us the best line of fit in some way. Because you do have, so again, you have 5,000 draws for beta 0 and beta 1. All of those contribute to the variability or the uncertainty about those parameters, right? So the best guess of this might just be the posterior mean. So then you take it. But you can also just like simulate many different lines based on the 5,000 draws that you have and see the variability across the different fits that you have. Okay. So for example, what you can do is, well, let's say, yeah. So I think I was using, right. So I'm using the cont'd package to get the draws. So I name it into the post, and then I'm going to just take the mean of the the beta 0 and beta 1. So I will get this, and then I will be able to generate like fits from there. So that's the code for what we're doing. And here I'm doing, so again, all of the dots are still just the data itself, but I'm drawing like 10 different lines. It's hard to see, but there are 10 different lines. It's the first 10 set of the beta 0 and beta 1. So there are 5,000 total because we have 5,000 that we drew from the posterior. But then this 10 over here is the top, like the first 10, I was in top 10. The first 10 from the draws, just to give you a sense of the variability, okay, among the different draws that you have. Okay. So in this case, I think we have close to 1,000 observations, so you actually don't see much of the variability between the draws because you have relatively large sample size. But if you have a small sample, then the difference or the variability between the lines that you're fitting might be vastly different from each other. Okay. So maybe whenever you, in your project or any other location, if you get a smaller data set and you're trying to fit the linear regression model to it, and then if you're going to try to play with those simulated fits from the model, you might see bigger variability because it's going to be a smaller sample size. So that's one thing. You can also learn about the expected response, and we know that expected response will be beta 0 plus beta 1 times x, okay, because that's the expectation. Okay. So what if someone just wants to learn about the expected log expenditure, And what they can do, not surprisingly, is you can obtain a simulated sample from this beta 0 plus beta 1 x by computing the expectation of each of the simulated pairs. So we have 5,000 pairs, right? And then we have all of the x that we have. So if you want to focus on the particular CU with a given xi, then you can actually simulate 5,000 different means for that observation based on what you have. You might not want to use all of them, but you can do it. And what we want to show you here is that, well, if I want to focus on maybe like 5 different, so the function here I wrote for you here is I want to use all of those draws, 5,000 draws. But I'm looking at different values of x. So remember, x is the log income, so we work on the log scale. In this case, I'm looking at what if the log income is 1 or 5 or 7 or 9. And then I'm trying to utilize the 5,000 different pairs. And then I want to show you the distribution of the expected value that it can take. Okay, so we're using this GG rigid package that can show you like patterns like this, that you're looking at log income of 1579. Each row is corresponding to a particular log income value. And then each row, as you can see, is actually plotting the density function, okay, of the expected value that you can get. So this is what we have, but I do want to pause here so you can digest what the plot is trying to show us. And do you have any takeaway messages from this result here? Okay, I would say think about like this it's 4 different density plots, right? They are centered at different values, right? And they have different spread as well. Okay, so what does that tell us overall? Check with your neighbors to brainstorm ideas here. Okay, so any comments, questions, takeaways from this plot? Is it useful or is it confusing? Anything is welcome? Yeah, Josh.
So I guess the fact that the distributions are like moving towards the right as the log income increases, that probably means beta 1 is like positive.
Yeah, and I think we just see that, right? Or yeah, I think it's right. So beta 1 is having a median of 0.4, and the 90% posterior probably like credible interval is around 0.4ish. Yeah. So yes. So the plot, as you can see, the mean or the center of the different density plots is moving to the right as you go up. That is saying that when you have your log income increases, it's a so beta 1 is positive because you're adding it up. And I guess in particular, you will have mean for log income. So xi equals to 1, then the the expected yi should be around like 4.8ish. That's what you see here. Right? And then this is about like 6.5. This is probably 7.25, I guess, and this is a little bit more than 8. Okay, so that's what the plot is about. Anything else from your discussion?
We were wondering why you see the pattern of decreasing variability. So if these are like predictions about log expenditure given log income, why would you be more confident in your predictions for households with higher log income?
Yeah, so let me just write that question maybe in the mathematical form, and I'll pose that for you to think about. So it is, so all of this, I guess, computing the expected value is trying to do the expected value of yi, right? So we're doing, which is mu I, which is the beta 0 plus beta 1 x I. Okay, so what we're doing, like we said over previously, is the pair of beta 0 and beta 1. So it's actually the same pair. Like I would say like 5,000 pairs, of course. But then for different values of xi, it's the same pair being applied to them and then computed. But we do see the feature, I guess, the spread of this expected value computation is decreasing, right? So you start with log like xi attribute 1, it's wider. But then as you go up, it's shorter. So what do you think that might be the reason? Okay. I guess we'll, oh, yeah, go ahead.
Well, just doesn't have to do with the, like, how much data we've incorporated into the model, because when we're at like log income 1, we've only looked at the points that have 1. We've only like tested them in our model, and we've only used xi where xi is 1. And so like as we increase, like the model is still like we're sort of like sifting through those coefficients and just using more xi's, and like it's arriving at similar and similar like proportional predictions. So it's a pretty
Do you agree what Zach says?
poorly articulated. But
I got it, yeah.
But I feel like we will have similar sample size when like income is equal to 9 or 5 or 7. It's not like we have more data about people who are richer or
Yeah, I guess this, yeah, so both comments actually go back to, I guess, how many observations, or not observations, I should say, how many values of the expected value that we're plotting here. Okay, so let me go back. So this part is only about the ggplot, but this is where the function here is how we're obtaining those expected values. Okay, so we write this 1_expected function, and what it takes is the values of x. Okay, and you can see that we're choosing 1, 5, 7, 9 just for demonstration. So what we're doing here is suppose is the data frame that is getting the beta 0, beta 1, and sigma. Okay, and then what we're doing is we're getting, so in theory there are 5,000 draws of them, all of them, triplet. Okay, so we're getting the x value multiplied with the beta 1 value, and then plus, which plus the beta 0, that's the mean, right? And then we put it in the data frame, and then try to plot it. So I guess in this case, we are plotting 5,000 expected values for each of the value of x. Okay, so I think that can clarify.
yeah, but like what I was saying was that but once we've hit 5, we've already plotted 5,000 once, and so we have an idea of what the model, like which the parameters, the density of the parameters from that. And so like we'll continually narrow is because we've done 5,000, then do another 5,000. And the model is still like the same. It's just, and we're just testing different coefficients with more values. So for the same coefficients with more values.
Yeah, so I'll leave that to you since the time is up, but this is a good question. And I think, yeah, worth checking. I mean, whichever way you can approach it, when we come back on Tuesday, we can continue our discussion about the spread here. We can clearly see the trend about the mean, and that makes sense, right? We can also clearly see the trend about the variance, but how to explain that in the model that we're doing, I think, yeah, so take some time, think about it before we don't do it.